think is 11.3. I think I'm going to try and focus over here because I'm not in the sunlight. If somebody feels too much sun, I can move around. I want to go at it. Students have trouble with log functions, right? And I think some of it is notational. Some of it is because there's some confusing things about it. But I'm gonna try and approach it kind of gently and see if I can kind of win you guys over that it's not such a big deal. So last time we looked at something called an inverse function. And the idea is you have like some x, you put it into some function f of x, and you get out a y, and then you take the y and you put it into the inverse function, and you get out the same x you put in. In other words, this inverse function undoes what the function does. And one of the nice features is that it works the other way. If you put some x into the inverse function and you put that output into the function, you still get the original number back. So you want to look at a particular function, a simple one. Let's just look at x and x squared. So let me put in a few members of the table. 1, 1, 4, 3, 9, 4, 16, 5, 25. That's enough. So if I write the table kind of backwards, 1, 1, 4, 2, 9, 3, 16, 4, 25, 5, I'm describing the inverse function, which just happens to be the square root of x. Okay, so that's the idea of inverse function. Now, the key takeaway today is that a log function is the inverse of an exponential function. We talked a little bit about exponential functions, and I'm going to do the same thing with the table here to give you an idea. So if we have x, my exponential function is going to be 10 to the x. So if I have 1, that's 1. Oh, sorry. Not correct. That's not where I wanted to start. If I start with 0, 10 to the 0 is 1. If I have 1, 10 to the 1 is 10. 200, 3, 1,000, and 4, 10,000. So now I'm just going to do what I did with the square function. I'm going to reverse. So I get 1, 10, 100, 1,000, 10,000. 0, 1, 2, 3, 4. So here, the function I'm going to write in is log to the base 10 of x. Now let's look at that. This is it's like a function of x. I've got this notation here we put down here. We call it the base. And that base refers to the number that the exponential function is raising things to. Now, apparently this is really hard. later on I'm gonna write something like this. I'm gonna write, what's the log to the base 10 of 10? The thing to do is to say, well, that's some number, x. Rewrite it as an exponential. Let's do this carefully. The 10 is the base. That's what we're raising something to. The log, that's this thing, is the exponent. And this is what 10 to the x is equal to. Where? Yeah, 10. So the question now is, if you look at it this way, I think it's pretty clear what x is, isn't it? Everybody? Anybody have any question about this? Does everyone like a little light go off? 1. It's 1. So the log to the base 10 of 10 is what? Another one. Log, this always kind of throws people off. Log to the base 10 of 1. I'm going to rewrite that. Here's my base. That's 10. There's my exponent. Yes, the log is an exponent. X equals 1. Okay, does everybody see what x has to be right away? It has to be 0. One more time, just for emphasis here. Log to the base 10 of 100. Someone want to think about that for a second? You think you have an answer? And you're not shy? If you think you have an answer and shy, don't do anything. If you don't think you have an answer but you're not shy, don't do anything. If you think you have an answer and you're not shy. Anybody? Yes?
Is it 2?
2. Everybody see that? 10 to the 2 equals 100. So whenever you see this and it's confusing, it's always good to think it through, right? Log to the base, we're going to use b when we don't put a number there to mean base. And I don't know, I'm going to call this n, that's x. That means what? B to the x equals n. I'm drumming that into you a little bit. That's because as soon as we get off this, you're going to have to refer back to this. Okay. Let's go for broke here. Log to the base 2. Oh, I changed it. It's not 10 anymore. So you don't want to panic. What can that be equal to? Well, 2, the log is an exponent, so this is the exponent, equals 4. So looking at it that way is pretty easy, isn't it? Log to the base 2 of 1/2. As soon as we get into fractions, it seems like it's confusing. But let's go for it. 2 to the x equals 1/2. Now, it might be simpler if I wrote 1/2 as 2 to the -1, right? And it's really obvious. Or if I said log to the base 2 of 1/8. Okay, so 2zx equals 1/8, which is 1 over 2 cubed, which is 2 to the negative 3. Okay, so this is negative 3. Okay. So that's what a log function is. It's the inverse of an exponential function. And although at first this notation is confusing, if you just translate it over to the exponential version, usually you can figure it out. It could, you know, I've just been giving you this as the variable, but if I said log to the base a of 9 equals 3, shouldn't use a, use b. Well, again, just looking at that, I can't, what is that? But if I write 3 to the base b, well, that wasn't what I was thinking of, but all right. Well, cube root of b is, b cubed is b, so this is the cube root of 9. It wasn't something nice. Can you have a weirdo base like that? Yeah. We'll get to a really weird base in a few minutes. Yeah. Okay. So, why logs anyway? By exponential functions. What do we want to do with? What do we want to do with these? Well, not that long ago, really not that long ago, when I was in high school, we did not have handheld calculators. We had calculators, but they were expensive and they were in the back room somewhere. We did not have computers. They had them, but we didn't get to use them. And we would take a science class, and we would do some experiment. And we'd have to, you know, multiply some numbers. I don't know, maybe do this. And we had to, you know, had to have a way to do it. And to go through this by hand is kind of tedious. This was a real thing. So how do we go about doing it? I'm wondering if I should, too much trouble. So what we used to have, we might have a one-page table, and it kind of look like this. 1, 2, 3, all the way up to 9. And it would be like, how would we do that? That's not right. A long time. 1, 2, 3, 4, 5, up to 9. And then we have 0.01, 0.0. Probably wouldn't have them all. Probably have 0.05, 0.10, all the way down to 0.95. And if you had a number like this, it's called a log table. You'd have like a number 1.01, 1.02, 1.03. You'd have the log of that number here. So 2.35, you kind of look up the log. Guess I didn't really explain why you would do that. I have to backtrack a little. We have certain rules for dealing with logs. There's a few of them. I'm just going to go over them really briefly. The way I want to do it is I want to do it next to the exponential form. So we have a law of exponents that goes something like this. A to the x times a to the y is equal to a to the x plus y. Right? Should have made that b. It's a base. So the way it works with logs is log to the base b of x plus log to the base b of y equals log to the base b of x times y. That's interesting. Here, I multiply by adding exponents. Well, what are logs? They're exponents. Here, I multiply two numbers by adding logs. Now, if you think about it, there's two steps to this process here. I want to multiply these two numbers. I first have to find the log of 2.35. I add it to the log of 5.76, and I get some number. And then, with my table, I kind of look it up backwards. Really, what I'm doing is using the exponential function. You go backwards. The inverse does. So, I guess we can do this here. So if I find, I haven't done this in a while, because we don't need to do it anymore because we have calculators, but I find the log of 2.35, and I add it to the log of 5.76. I get 1.1131 something or other, and now I'm going to raise that to 10. 10 raised to whatever I just got, and I get 13.536. Well, is that about right? Yeah, that's about right. The thing about log tables is if you had like, instead of 2.35, you had like 23.5, you'd have to use the same table. It's just, now like, moving the decimal over is like adding 1, so you have to keep track of that yourself. So we used to do this. What about division? Well, the log to the base b of x minus the log to the base b of y, log to the base b of x divided by y. That's nice. I can just convert everything to logs and do addition and subtraction. It works even better when you're doing, like you're raising something to a power. Log to the base b of x to the a is just a times the log to the base b of x. So if I try to find x to the a, I find the log of x, and I multiply it by a. Now I still have a log at that point. I have to go backwards to get my answer. The nice thing about this, if you're squaring something, right? Okay, it works really well. But what if you want to find like the cubed root or the fifth root? Well, finding the fifth root is something that seems pretty hard. But with a log, you just multiply it by a fifth, and then find the inverse. So that's, historically, that's where logs came in. We don't We don't need that as much anymore because we have handheld calculators. Some of the calculations that go on inside a little computer involve finding a log. It's easy to do that. All right. I'm not really following my notes very closely here, but I seem to be covering everything I want to cover. All right. Now, just a word about the base. When we would do calculations in chemistry, we were always doing base 10, because then if I had a number like 23.5, I could just look up the log of 2.35 and add 1 to it. 10 to the 1 is 10, right? Or if I was using, like a number less than 1, I could move the decimal over and subtract some number of ones. When we're not doing something like that, you really can use any base you want and it'll work. Those of you who have seen like a TI calculator, you may notice that there's a button here that says log, and log usually just by itself, no, actually, this isn't that important, but so if you're a scientist, log means log to the base 10. There's this other thing, it's called ln. And no matter who you are, that means log to the base e. E is about 2.71828. You may remember when we were doing financial stuff, we were doing compound interest, and we wanted to find the future value on some investment where we're doing interest, and how did it go? Principal 1 plus n to the ny. I think that's how we do it. Interest. So if you want to, calculate yearly or bi-yearly, you can use a different n. If you wanted to calculate interest continuously or infinitely, it was f equals p e to the iy, where that number showed up. It's the same e, which is to say log to the base e of x is the inverse function of e to the x. And it's on a calculator, so that tells you it's probably pretty important. On the calculator, it's ln. Now, I say this because if you're a mathematician and you see log, it means log to the base e. I don't think anyone here has to worry too much about that. Wait a minute. See, log is log to the base e. And if you're a mathematician and you wanted log to the base 10, you have to say log to the base 10. We could also say for log to the base e ln. All right, it's a confusing thing, but for us, log is the same as log to the base 10. All right. And when you're doing this kind of calculation, it doesn't matter what the base is. So if there's some calculation you want to do on your calculator and you hit the ln key, that's fine as long as you know, its inverse is not 10 to the x, it's e to the x. Okay. Now, we went over inverse functions very quickly, but you may remember that I told you that, I think I need marker. Oh, why not? Wild here. I think I told you that if you graph a function, like, let's say we graph f of x equals x squared, of course it's a parabola, and you graph its inverse, which is the square root of x, that these two functions are kind of mirror images of each other. If you think of this line here, y equals x as the mirror. Did I lose someone?
I think they were to the bathroom.
Are you asking? I'm sorry.
Oh, no, they went to the bathroom.
Oh, someone went to the bathroom. Who was it? Because I don't have them marked as here.
I don't know.
Oh, it was Paolo? Paolo? Okay, I missed. Who was here? Oh, no, it was Kate, wasn't it?
Kate, yeah.
Kate, yeah, okay. Okay, all right, there we go. Well, this is going to be true with exponential functions. What should I erase? I'm going to erase this. This is true of exponential functions too, and they're log functions. So let's take a look. An exponential function, let's try and graph 10 to the x. So at 0 it's 1, and at 1 it's going to be 10. And at negative 1 it'll be 1/10, and it's going to taper off here. So the inverse function is the log to the base 10 of x. I guess that's 1, all right? And this is 1, too, so it should probably be a little higher up. Okay. So the log function is going to go through here, and it's going to go this way. And then it's going to, come and taper off here pretty quickly. At negative 1 here, it'll be just a 10th, so let's see if I can draw that a little better. And just like with any other inverse function, the image, the graph of the log function is again the mirror across this y equals x of this function. So if you're asked to graph a log function, one reasonable way to go about it is first graph the exponential function and then just kind of use your ability to mirror image. Is there something else to say about that? Think about that for a second. Yeah, there's something really interesting. case anybody's interested, actually have a picture. I wouldn't do this in any other class. But you know, I'm not making it up. He actually had a log table. Now, can you guys in the back kind of get a feel for this? Now, don't laugh. This is one page. These are what we call 5-digit decimals. Instead of, you know, what I showed you before, we only had three numbers of accuracy. These would actually have 5 numbers of accuracy. But the book that this came in was like 100 pages. So to do a calculation, we'd be flipping through the book and then looking down on the table. I guess the other thing I wanted to mention is, I don't know if you can see in the back. Does anyone, I'll show you guys in a second. Anyone see this thing here? Has anyone ever seen one of these? It's called a slide rule. Okay, maybe if I remember Thursday, maybe I'll bring one in. The way a slide rule worked is the numbers on it were placed apart using the log function. So if you would move the slide back and forth, you were adding, but you're adding logs. So we actually, you know, in science class, we just wanted 3 digits. We could just use one of these and very quickly, we could, you know, multiply and divide. All right. All right. If I have time, I'll do the thing that I think is really interesting. Okay, so working with logs, and this is probably would be the best kind of stuff to take away from this class. If you're gonna take a chem class or a biology class, or you know, if you need it for statistics, but just like we have laws of exponents, we have laws of logs. So I'm just gonna, I think we've almost covered all of them already, but let's just break them all down. So for exponents, a to the 0, where a is not 0, is 1. So we have this log, that log to the base a of 1 is 0. That's a useful thing to know. A to the 1, of course, is equal to a. So log to the base a of a is 1. Now this one's going to look a little funny, but a to the x is of course equal to a to the x. That's not saying much, right? But the log version of this is log to the base a of a to the x is x. Now, before I go further, I just want to point out, remember, log to the base a, if f of x is log to the base a of x, its inverse is a to the x, or vice versa. So all I'm doing here is what I was showing you at the beginning. I'm taking an x, I plug it into this, right? I get a to the x. Then I do the inverse function on it, log to the base a, and I get back x. That's true of any inverse function, but in particular, the inverse of a to the x is log to the base a. So that's why this works. Now, I think I mentioned that you can do this with either f inverse of x equals x, or f inverse of f of x equals x. There's kind of a symmetry there. So for this, there's a I can do the same thing kind of in the opposite. It looks like this. A to the log to the base A of x equals x. And these are, you can think of these as identities. Sometimes they're useful for simplifying expressions. They can be handy. All right, now for the computational stuff. We already kind of looked at a to the x plus y is just a to the x times a to the y. That's our law of exponents. Our law of logs is log to the base a. Remember, that's the base of x plus log to the base a of y is log to the base a of x times y. And we have the equivalent subtraction. A to the x minus y is a to the x over a to the y. So the log to the base a of x minus the log to the base a of y is log to the base a of x over y. And finally, we have this exponential idea. Log a to the x to the b, according to our law of exponents, is a to the xb. And the equivalent law is log to the base a of x to the b is b times log to the base a of x. That is, if you have an exponent here, you can just move it in front if you're doing the logs. All right, all this would be kind of abstract and kind of useless if we didn't have a few examples. So, how about this? This would be like if I was giving you homework on this. If I was giving you homework on this. I guess I have to cop. In fact, we're too late in the year to give you homework. But log to the base 2 of 80 minus log to the base 2 of 5. Let's say I wanted to simplify that. So my first step is to use the subtraction law. That tells me this is log to the base 2 of 80 over 5. Well, that's log to the base 2 of 5 into 8 is 1, into 30 is 6. That's log to the base 2 of 2 to the 4th. That's one way to do it. And I can move this in front. That's 4 log to the base 2 of 2. And I thought I had log here. Log to the base a of a is 1. Ah. Log to the base 2 of 2 must be 1. This is just 4. So that's how you would you could simplify this. Kind of fractal it right down here. Okay, we'll try this one. Log to the base 5 of x cubed y to the 6. Well, I don't know what x and y are, but it might be simpler if I didn't have exponents in this. So this is log to the base 5 of x cubed plus log to the base 5 of y to the 6th. And again, using this trick, I can move my exponents into the front. This is going to be 3 log to the base 5 of x plus 6 log to the base 5 of y. I think that's enough for this class. If you go on to pre-calc, you'll come back and you'll have to do a lot more work and a lot more homework than we're doing here. But that gives you just enough introduction. If you feel like you're gonna need this before you take a pre-calculus class, I recommend 3 things you remember. Log functions are inverse of an exponential function. A log is an exponent. Keep that in mind. So when you convert from here to here, the log tells you, we always say log to the base A, or log to the base B. So you know what the base is, you know what the exponent is, you can reverse it. And these laws of exponents are useful for manipulating. That's the best. So, before I let you go, I'll just remind you, we're going to have has to be kind of brief introduction on Thursday for statistics. So if you're going to be taking a stats class, this will get you a leg up, small leg, and that's really it. Next Tuesday we'll have a review. Definitely, if there's anything in your homework you ever wondered about, bring it in. I'll bring the book, I'll go over some problems. Oh, I posted a review sheet. Before you go, let me just get that. I posted this on Canvas. It says, you should know for the final, everything on the midterm 1 review sheet, everything on the midterm 2 review sheet. You just have a list of a few items. Of course, for the calculator, of course, for the exam, you may bring a sheet of paper with notes, double-sided, right, as small as you can read if you wish. You find the more you write, you know, it's diminishing returns. If you're a business or an economics major, you know about diminishing returns. Too much information, you spend too much time looking for it. So put stuff that you think you'll need to be your memory jog. And you can bring a calculator, not a cell phone calculator. A calculator, if you don't have one, I will have some TI calculators you can use. Okay, thank you. Thank you, everyone.